This is lesson 11 of industrial instrumentation. In this lesson, we will study the capacitive transducers. You see the capacitance transducers, the contents of this lesson, capacitance transducers as a whole, displacement transducers, capacitance transducers in the sense that a basic principle of the sensor we will discuss, and capacitance transducers are basically used as a displacement transducers, level gauge or level sensor, both liquid and solid, differential pressure transducers, because these differential pressure transducers are utilized in the, we will see in later on in the flow measurements, and the DPT or differential pressure transmitter is basically a differential capacitive transducers. Then we have pressure pickup. We will also discuss the pressure pickup, as well as we will solve some problems also, right. And at the end of the lesson, the viewer will know the basic principle of capacitance sensors, linearization of the sensor, differential measurements, right. This basically we will discuss in this. Now, see the capacitive transducers, a capacitor consists of two conducting metal plates separated by an insulator, right. These metal plates can be either just a rectangular plates, very thin rectangular plates, or it can be a cylinder also. It looks like that, you see, it can be a just two parallel plates like this one. It could be a two parallel plates. Okay. In between we have a dielectric, right. And so it happens that the capacitor consists of two conducting metal plates separated by an insulator or dielectric medium. When a voltage is applied to the metal plates, equal and opposite electric charges appear on the plates, right. And interestingly, this can be a these plates can be a cylinder also, that we will see in later on. It is not necessarily it can be it should be rectangular, it can be circular also. The plates might be cylinder also. That means it can be have a sensor like this. So one plate is like a one cylinder like this one, and inside there is another plates which looks like this. So this is another. So we can take out the from here and here two terminals, and if you measure the capacitance, this is also a capacitance sensor. The ratio of that charge to the voltage is the capacitance. Now, see the capacitance of a parallel plate capacitor is proportional to the area A of the plates. Okay. Area can be anything, can be the can be circle, can be the cylinder, and inversely proportional to their separation D. Separation between the plates are D. In the case of cylinder, it will be separation which is the difference of the outer and the inner radius of the two plates. And neglecting fringing, you know the fringing effect is there always in the capacitance. If we explain, that means it lies that if you have two plates, always it will like this one. Suppose I have a plates, two plates, so the lines will be like this one, okay, and the end, since it will repel each other, so it will be straight, but this will be like this one. So if we, this is called the fringing effect, and actually for the fringing effect exactly you cannot get mathematical expression for this fringing effect, but if you neglect the fringing, then the mathematical expression of the capacitance looks like this. C equal to epsilon naught into epsilon r A by D farad. F is farad. This F is basically farad, and where epsilon naught is the permittivity of free space, it is a vacuum, and with a value of 8.854 10 to the minus 12 farad per meter. Epsilon r is the dielectric constant of the material of the gap. For R, epsilon r is equal to 1, and A is the area, so it should be in meter square, and D is in meters, right. The capacitance is a function of a shape, and so we can see that capacitance is a function of a shape and size and permittivity. and alterations of A, D or epsilon r causes a change in capacitance as shown in figure 1. We will show the figure 1. So, that means you can see that if either of these one, either A, D or epsilon r changes, we will get the change of capacitance. Okay. So, if you measure this capacitance value either with a bridge or in some LCR meter, so that change can be utilized to make it a displacement sensors, pressure pickup and level gauge. So, these are the three basic applications of the capacitive transducer. So, if we can measure the change in capacitance value, it can be utilized as displacement, level and differential pressure sensor. This actually I want to tell. Now, here you see there are various type of capacitance we have shown. These are basically as a displacement sensor. You see the two area between the X and Y are cylinders. You see these X and Y are cylinders basically, X and Y. And you see the dielectric medium might be air also, there is no problem. So, if I push it this way, you see if I push this Y, X is a fixed plate, X is a fixed plate and Y is the movable plate. These two can be cylinders. If I push it like this one, it can be a simple parallel plates also. Suppose I have two parallel plates, right? You see here, suppose I have parallel plates, two parallel plates. And if I shift these parallel plates, suppose previously it was in this position, now we have shifted this position. So, area between this one has changed, is not it? Previously the area of cross section was A, now it will be less, only this much of area is there. So, we can see that the excuse me, that capacitance has been changed due to the change of area. Okay. Instead of taking plates, I can take two cylinders also. So, where if I vary Y, that means this way, so the capacitance value will change. This capacitance change can be measured by some LCR meter or by some bridge. So, that capacitance change can be calibrated in terms of the displacements, as simple as that. Now, you see the D can be varied also. That means the separation between the plate, this is the separation, this is actually, if you look at, this is D, right, this is our D. So, the D can be changed also. If I change D, obviously what will happen, the capacitor will also change. The more the value of D, so the less will be the value of the capacitor. So, quite obviously this can be also utilized to make a displacement sensor, right. So, here the area between the two plates changes. Plates can be either plates or can be two cylinders. Here the distance between the plate varies. So, both way the capacitance change will be there. So, that can be utilized to make our displacement sensor. Now, geometrical variation you see here, actually what will happen, you see instead of the displacement between the plates or the area between plates, now the permittivity between the or dielectric medium between the two plates are varied. You see here actually these are the two plates, actually this is the those who are familiar with the heterodyne deceivers, you know that in the heterodyne deceivers we are our radio deceivers, we change the capacitance value to tune different radio stations. So, basically what will happen there, actually I am changing the permittivity between the two plates, because these plates, if you look at very carefully on the screen, on this one, see these plates, you see here this plate, this moves, this is a dielectric medium, it might be plastic also, insulator, obviously dielectric medium has been insulator. So, this will vary in this position, so the plates are fixed. If the plates are fixed, neither area between the plates changes, so only the dielectric medium changes. Okay. So, what will happen if I take it out, you see that there will be more air between the two plates and there will be less that plastic, I mean that between the plates, and if I move it this side, so because it is semicircular plate, entire separation between the two plates will be filled up by this plastic. So, the epsilon r, if you look at C equal to C naught epsilon naught epsilon r A by D, what we said in farad. So, this epsilon r will change. So, this epsilon r if changes, so obviously I will get a different value of the capacitance. Here actually what we are doing, that we are changing the permittivity between the medium, right. So, by changing the permittivity, either permittivity or area or displacements, I can get the capacitance sensor. Here you see in the this is another example of a liquid level gauge. You see the it is cylindrical in shape, right, and we have a one inner rod also, right. So, this inner rod will consist one plate, this is one plate, and this cylinder, outer cylinder will be another plate. Now, if we pour liquid here, you see the dielectric medium between this plate and this plate consists of two different material. One is air, another is the liquid, right. So, if the air, if it is more, if you fill up this this tank, what will happen? You see that there will be more liquid in the tank and less of air of the in between the two plates. So, the dielectric medium changes. So, obviously, what will happen? The capacitance value will also will change. This principle, this method, this can be utilized to make a level sensor or level gauge, and this is very interesting that this can be utilized to make a level of solid as well as for the liquid, right. Now, this all in all the previous cases we have seen that this output is single ended output, right, but we always prefer differential output. There is some advantage of the differential output because nonlinearity will be less. So, different and the output unbalanced output, because ultimately if I want to make a very accurate measurements, please note that I have to put that capacitance in a bridge. See, if I put in a bridge, so if due to displacement or due to permittivity change, that means due to area change, permittivity change, or the displacement between the separation between the plate changes, what will happen? Your output will change, right. But in the case that if this output is more, that will be always better for us, because that will simplify our measurements. Exactly that thing we are doing in the case of differential output. You see the capacitance change can be C plus minus delta C or C plus minus plus delta C, all the same. You see here the X and Y and Z are cylinders, area between the plates vary. Now, you see here I have a capacitance between this plate and this cylinder and this cylinder, again between this cylinder and this cylinder. Now, if I shift this cylinder on this side, what will happen? Area between this plate and this plate will increase, and area between this plate and this plate will decrease, right. Now, you see if it is exactly in the geometric mean position, then what will happen? The capacitance between X and Z and capacitance between Z and Y will be identically, should be equal, right. That means capacitance between X and Z and capacitance between Y and Z should be exactly identical. Now, if we push it on this side, then what will happen? You see here, if I push this one this side, then what will happen? That capacitance between X and Z will increase because it is getting more area between the plates, and capacitance between Y and Z will decrease. Similarly, if I put on these directions, the capacitance between X and Z will decrease, and because the area will be less, and the capacitance between Y and Z will increase, right. So, if I put this in the two arms of the Wheatstone bridge, obviously my bridge unbalanced output will be double. So, that is the advantage of using the differential measurements. This is a differential output from a capacitance sensor. Here also you see that I have two plates, fixed plates P and Q, and one movable plate is M, right. So, I have a displacement separation between the two plates are D, and if the area is, these are all parallel plates, if the area is actually if the exactly area is D here it is D, here it is D, then what will happen? The capacitance between this M and Q and capacitance between P and N will be exactly same. If these are exactly at the mid position, so the capacitance between this and this and capacitance between that means capacitance between P and M, capacitance between Q and M will be identical. Now, suppose I push this plate M slightly upward by displacement of X meter, then what will happen? You see, if you displace, the capacitance between M and Q will increase and capacitance between M and P will decrease. Again the same advantage I am getting, that if I put in the opposite arm of the Wheatstone bridge, I will get the more unbalanced output, right. Here the distance between the plate varies, geometrical variation, again the same thing, that means I am getting differential output here, right. Now, X, W, X, Y and Z are cylinders. Now, in this case you see the permittivity variations, variable capacitor with differential output. You see what will happen here, this M, this is Z basically, right, this outer bigger cylinders. We have capacitance between X and Z, X is a solid rod, Y is also solid rod, and that Z is a cylinder. So, what will happen normally between, I have capacitance between X and Z and capacitance between Y and Z. So, if the dielectric medium, now here the dielectric medium or the W I am varying, that means its position is getting varied. If the position getting varied, then what will happen, you see here, if I move it in this side, so there is a more dielectric medium between x and z, and there will be less dielectric medium between y and z. So the capacitance between these x and z will increase and capacitance between y and z will decrease. Similarly, if again this dielectric W is we shift on the right hand side, suppose I am shifting it on the right hand side, then what will happen? That means if I show it like this, if I shift this on right hand side, then what will happen? The capacitance between W and Y, because I am getting more dielectric medium, so capacitance between Z and Y will increase because I am getting more dielectric medium, and capacitance between X and Z will decrease because I will get the less dielectric medium. So this again I am getting a differential output. So the capacitance can be, you can utilize as a displacement sensors, and you can have a single ended output, also I can have a differential output, right. One or more of the plates are not connected to ground, and therefore electrostatic screening is required to avoid pickup, because capacitance measurements, because these are basically the value of the capacitance are very small and there is always stray capacitance. So all these things you have to take care while you are making a signal processing circuitry. Usually this 50 cycles main supply frequency always be picked up, so we have to use proper shielding to get the capacitance value. The screened cable connection to the capacitive sensors can be source of error, because it might change its capacitance when there is a movement between the cable conductors and cable dielectrics. So let us now go to the instrumentation lab and see some capacitance based sensors. This is another application of the capacitance sensor which can be utilized to measure the displacement. Usually capacitance sensor based on the three different criterion. One, you can vary the area of the plates, you can vary the displacement between the plates, that means separation of the plates, and also you can vary the position of the dielectric medium inside the capacitor. The particular gauge which you are looking at now is basically depend on the displacement. You see, if you make the displacement here, the separation between the capacitor plates changes. So obviously, if the separation changes, the capacitance value also will change. So that so if you put in a bridge, so obviously the bridge unbalanced output also will change. So that bridge unbalanced output can be calibrated in terms of the displacement, because ultimately we are not measuring the capacitance, we want to measure the displacement, which is our input, that is converted to the change or variation of the capacitance, and ultimately which will give you some unbalanced voltage. These are another applications of the displacement sensor based on the capacitance. Welcome back to the classroom. Now you see that we have seen some sensors already in the laboratory. So we have observed, you must have observed that the variation in area A or separation D requires physical connection to the moving part, while permittivity with epsilon r variation does not, because you see it is not very simple. I mean, even though I am showing in the diagrams, I mean two plates are there and we are making the separation, physical implementation it's not that easy. It's quite difficult to have that type of making connection, that two plates will be exactly parallel to each other while you are making the separation. That means plates, two plates are like this one. If I see two plates are there, so if I make a separation like this one, I will get a different value of the capacitance. But actual implementation, it's not very easy. It's quite task. Plate might be this way or that way. So entire mathematical calibrations, entire calculations will be wrong. So the calibrations also will be different. Okay. Similarly, area also. If while changing the area, two plates will be parallel plates, so it should be exactly parallel. But in one fixed plate, that is separate thing. But once it is movable, it is very difficult to keep the parallel all the way along, all the way in the entire range of the movement. So all these things you have to think of, right? But in the case of permittivity, there is no such problem arises, because it's simple. There is no change or mechanical change of the systems, most of the cases, especially in the level gauge you will find this is very much true. But other cases, while I am showing one differential, that we are changing the another cylinder by changing the permittivity, that is also the same problem we will face, right? with the variation in A or epsilon r have linear operating range, so is usually 1 to 10 millimeter, although the capacitance transducer is mostly used for small displacement where D varies. So, it's usually it is used for the very small displacements. It works for a very, for larger displacement we have many other sensors like potentiometers, presets and all these things. Usually we can use this capacitance sensor for a smaller displacement measurement. The most common form of variable capacitor used in the displacement transducer is a parallel plate capacitor with variable ER gap. So, just simple ER gap in between, and I am varying the separation between the plates that we have seen in the laboratory. The problem of nonlinearity between the distance and the plates D or capacitance C is shown in the following figure. You know that if you can look at very carefully that the relation between the capacitance and the D is the change of capacitance and D is not linear, right. You see here if I take a see if I, because we have seen that C equal to epsilon naught epsilon r A by D, right. You can see these relations, obviously it is not, the relation between C and D is C is directly inversely proportional to 1 by 2. So, it is a nonlinear relations, because if you take a differentiation then you find it is a nonlinear relation, right. But we can see that with the use of simple op amp we can linearize it. This is very much necessary because in many applications we need this type of measurements. So, this is the op amp based circuit you see here that you are using one op amps, and this is the capacitance which will be variable. That means whether you are using as a displacement sensors, level sensors, it does not matter. We put on the feedback path of the op amp, and CF is the fixed capacitors. I am giving an excitation voltage of EX, okay, and taking the output from E naught. If we assume and E naught and ground, if we assume that this ideal op amp, it is offering a large input impedance, so that it is not drawing any current, whatever the current coming in is flowing through this path. So, quite obviously immediately I can write the output voltage like this. I can write the output voltage like this. This is this is an ideal op amp. If you take, assuming the op amp as an ideal devices, I can immediately write E naught by Ex equal to Cf by Cx, right. So, it is E naught by Ex equal to minus Cf by Cx, right. And quite obviously where C is the fixed capacitor, Cf is the fixed capacitor, Cx is the variable capacitor or capacitance sensors actually, and immediately what we can write E naught equal to Cf by D epsilon naught epsilon r into A. So, you see that we have linearized it, the output voltage is linearly proportional to D. So, our measurements becoming more simple if we use this type of arrangements. But obviously, if I want to, in this case, if I want to vary A, that will not be a very good proposition, because in this case you will find it is again becoming inversely proportional to A, output voltage is inversely proportional to A. But many situations we will use only D or the separation between the plates that can be utilized to make our sensor. So, obviously, output voltage will be proportional to D. It is clearly seen that the output voltage is now directly proportional to the plate separation D. Thus, linearity is achieved for both large and small motions. In commercial instrument, this EAX excitation is 50 kilohertz sine wave of fixed amplitude. Okay, amplitude is fixed, right. The output E naught is also a 50 kilohertz sine wave. This will be wave. I am sorry. This will be wave. This will be wave. So, in a differential capacitance pressure transducer, the plates are circular. Plate M is thin diaphragm across which the pressure differential will go. I think I have skipped something. Let me go back. no problem. If I go, yes, yes, yes. So, in a differential capacitance measure pressure transducer, the plates are circulars and plate M is, the figure will come in the next slide. Plate M is a thin diaphragm across which the pressure differential to be measured is applied, right. With equal pressure applied to the both pressure ports, that is diaphragm is in the neutral position and the bridge is balanced and the output voltage E naught from the bridge is 0. How does it look? You see, this is our example of our a differential pressure pickup. You see here, this is our movable plates. This plate is movable plates. Okay, it is moving in this direction or this direction. If this pressure is higher than this pressure, okay, this pressure is higher than this pressure, so the diaphragm will be stretched in this direction. It will look like this one. And if this pressure is higher, then the diaphragm will be stretched in this direction, right. And X and Y are the fixed plates. Actually, this is, if you look at, it is a section of a sphere. Actually, if you look at the section of a sphere, and this inner side is coated with the metals. So that coating will work as a plate of the capacitor. Now, this type of pressure transducers as a differential pressure transducer has a tremendous applications in modern day instrumentations. You will find everywhere. I am using flow sensors, and flow sensors, as you know, in the most process industry, these are huge in number. And in all flow measurements, especially our in the case of orifice meter, Venturi meters and pitot tube, we use some differential pressure pickup, because this sensor, this output is to be transmitted to the control room, and this signal is to be transmitted to the control room. So, I need this differential tapping. It looks like this one in the flow measurements. Why this is important? You see, we have a pipe here and this orifice, we will discuss orifice later on. So, we have a tapping here, we have a tapping here, right. So, liquid is flowing like this one. So, there is a high pressure, this is high pressure area port and this is low pressure port. This high pressure port, if it is connected here and this low pressure port is connected here, then what will happen? This diaphragm will be bent like this one. And then what will happen if it bends like this one? Since I told you this inner side is coated with metal, what will happen? This is a section of a sphere. So, inner side is coated with a metal, then what will happen? You see, these plates will move this side and the capacitance between this plate and this plate will decrease, and capacitance between this plate and this plate will increase, or capacitance between X and A will increase, capacitance between M and Y will, capacitance between X and M will decrease and capacitance between M and Y will increase. So, if this differential, if you put on a bridge, we will see in the next slide, if you put on a bridge, I will get a large bridge balance output that can be converted to the current of 4 to 20 milliampere and transmitted. That 4 to 20 milliampere of current will be corresponds to the 3 to 15 psi of pressures, right. So, that is the reason I am saying stretched stainless steel diaphragm movable plates or capacitors. Actually, in the process you will find that we are using pressure capsule, actually capsule, so that it is not necessarily directly you have to give, the pressure will come down here, because this liquid will directly come down here. So, in between there is another liquid, so that it will in turn make a pressure on this side, so that it will be stretched like this one, right. Now, see, this is our signal conditioning circuit, it is the bridge circuit of the differential pressure pickup. We have X and Y and M movable plates and two capacitors. What will happen? If this is increases, this will decrease. That means, if this increases, I am sorry, if this increases, let me go to the previous slide. Yes. So, if one pressure is greater than the other, so obviously what will happen? The diaphragm deflects in proportion and giving an unbalanced output at E naught and in proportion to the differential pressure, quite obviously. For the opposite pressure difference, E naught shows a 180 degree phase difference. What is that? If you look at very carefully, you see here, what will happen, you see here that if I put on a bridge, so it is very difficult to know if I look at, because if this is if the diaphragm moves in this direction, then what will happen, the capacitance between x and m will decrease and capacitance between m and y will increase, right. Now, if the capacitors, if the suppose pressure on this side increases, so the diaphragm will stretch like this one, diaphragm in that case will be stretched like this one, then what will happen, you will find that the capacitance between this and this will increase and capacitance between this and this will decrease, right, is not it. So, therefore, a phase sensitive demodulation is necessary, right. Even though I am saying, you see that I am saying that like this one, let me see. So, I said that I have a capacitance here, I have a capacitance here, right. So, if I put a signal here and measure the output voltage E naught here. So, if this is increases, this will decrease, that is no doubt about that. So, I will get an unbalanced voltage, right. Now, if this is decreases and this increases also, I will get unbalanced, but how will I know that which side it is? So, for that reason we have seen as we did in the case of LVDT, I need some phase sensitive demodulation. With the phase sensitive demodulation, this type of problem can be easily solved. Now, see, this method is basically, I should tell that this method is basically for, therefore, this method allows measurement of static deflections, because if it is a static deflection, so I can easily measure by this type of method, right. Such differential capacitor arrangements also shows the considerable greater linearity than do the single capacitor types. You will find that the linearity will be more in this type of capacitance arrangement, right. Now, capacitor's pickup or capacitor microphone is a very important devices. Okay, I mean, you will find that it is basically a capacitance sensors, and the separation between the plates changes in that type of situations. You see here, this is a capacitance sensor, this separation between the D will change, and I am measuring the output E naught. Now, only problem with this type of capacitors that pickup is that it is only for the dynamic displacement measurements. For static displacement measurements, I won't get any output. I am using an excitations of Ex, E subscript Ex. So, what will happen that if there is a, if this is fixed, so there no current will flow through the capacitors. Okay. So, I will get the, I won't get any output. Whenever this moves, okay, as it happens, once I talk, this microphone works. You see, this microphone is also a capacitive transducers. You can see here, this microphone is also a capacitive transducers. So, when I am talking, so this capacitance between the plates in changes, so I will get a output here, right. We know that, you see that we have already seen, because you see what it happens that C equal to, I said, equal to epsilon naught epsilon r A by D. So, from that equations I can write delta C by delta D, C by D, right. Similarly, delta C by C, delta D by D, right. So, that means, sorry, this will be delta C by C, this will be no delta C will be there. So, delta C by C by delta D by D. So, when the capacitor plates are stationary with separation D naught, no current flows and the output voltage will be 0, as I told you earlier, right. If there is then a relative displacement Di from the position DO, a voltage E naught produced and is related by these expressions E naught by D, K D, tau D plus 1. As you know that, sorry, I am sorry. Should go away. I think I should escape from here. So, what will happen, you see that this is our magnitude and phase plot of the capacitance sensors. You can see here that magnitude is E naught by di, because E naught is the input, di is the E naught is the output and di is the input, right, as from the nominal position. So, I am making, and Ex is the excitation, that is not a, I mean that is not the input to the systems, and the phase plot will be like this, magnitude plot will be like this one, and the phase plot of this one will be look like this one, right. So, you can see here that the frequency range of this one will be after some certain point. There is a large phase shift at the beginning when the omega is low, otherwise there is a, I mean as the frequency increases. So, we can see here this is also please note this is also omega. As the frequency increases, the phase shift also becoming 0, and your representation or of the original signal also will be better and better. Now, as I told you, as I told you earlier also, this arrangement does not allow measurements of static displacement, since E naught is 0 in steady state for any value of di. For sufficiently rapid variation in di, however, the signal E naught will faithfully measure the motion. You can see that E naught by di j omega k j omega tau upon j omega tau plus 1, where tau is the time constant of the systems. For omega tau much greater than 1, right, instead of omega I am writing omega tau, if omega tau much greater than 1, E naught by j omega equal to k, right. So, microphone usually need not measure sound pressure smaller than 20 hertz, because usually we talk between 20 hertz to 20 kilohertz, that is the reason we are talking all musical instruments also within this range 20 hertz to 20 kilohertz. So, above so arrangement is perfectly satisfactory, because as you have seen the plot, phase plot and the gain plots, the low frequency production is not very good, but the high frequency is quite good. So, if you go above 20 hertz, so there is a faithful reproductions of the original signal. Our goal is to reproduce the original signal, that means the sound pressure on the microphone. To make omega tau much greater than 1 for low frequency, it requires a large tau. So, to make, how can I make omega tau much greater than 1? Only if the at low frequencies, only possibility is tau will be much greater than 1, only then in that case it will be more than 1. If it is more than 1, so I will get the input output, my relation is the input output relations will be k, that E naught by d will be equal to k, approximately will be equal to k, is not it? So, that is possible, right. Now, then we can see it again here, you see that we can go back. You see here, so no problem. You can see here that if this E naught by di is better and better, faithful reproductions of the original signal. So, omega tau for low one, yes. For a given capacitance and D naught, the value of tau can be increased only by increasing R. Typically R will be 1 megohm or more. So, if you can make 1 megohm or more, obviously omega tau will be quite large. So, even for low frequencies, so I can faithfully reproduce my original signal, right. Thus, to prevent loading of the capacitance transducer circuit, high input impedance amplifier is required, a buffer amplifier is required. So, there are various types of buffer amplifier, it is not very big deal now to have a good buffer amplifier. So, we can have a good buffer amplifier and can make the reproductions. Capacitive sensors now widely used for, as I told you earlier also, for the labels of liquids and the solids in powder or granular form. So, sensor is suitable for use in extreme conditions, liquid metals at high temperatures we can measure it, which is not possible in other liquid gases. Low temperatures also we can measure. Corrosive liquids like acids and all these things where or caustics where it is very difficult to measure with any other sensors, but capacitive sensors is very easy. You can have two stainless steel containers, and within that I can pour some corrosive liquids and make the level measurements. High pressure process where the other sensors will fail, in that type of situations also capacitive sensors work very good, because it is totally independent, measurements totally independent of the pressure of the liquid. Right. Now, we will solve some problem, so that for the digital class let us look at. So, the problem is like this one. You see, we have we take a we will solve some problem later on also. Problem 1. Problem is like this, that I have a sensor right. Rather I should first draw this it looks like that. I have a capacitance, a differential capacitor, sorry, differential capacitor like this one, right. So, separation is D, this separation is also D. Okay. So, there is a movement of this one, which is we are assuming delta D. Right. This is problem number 1. Right. So, I have plates. So, this is also I am taking connection. There is another connection, and there is another connection here. So, this will be C1 will be equal to C naught. C naught is the when the capacitance plate is exactly at the mid position, capacitance between the two are same. So, that is C naught plus minus delta C, and this will be C2, capacitance between this and this equal to C naught plus minus delta C, right. If I draw the equivalent circuit of this one, it looks like our goal is that is a variable area. This is a displacement type sensor, with differential output. Right, where area of the plate or the plates equal to A meter square, D is the nominal separation between the plates, and epsilon is the permittivity. Actually, in this case we have a combined epsilon naught and epsilon r. So far the text whatever we have discussed, epsilon naught and epsilon r, we have combined in epsilon here, right, no problem. And delta D is the displacement. It is a displacement sensor. So, delta D is the displacement, right. Now, what you have to do, calculate Number 1, calculate delta C by C naught, where C naught the nominal capacitance and delta C is the change in capacitance corresponds to delta D, right. Also we have to find number 2, show that the output voltage E naught is equal to V by Cf C naught to delta D by D upon 1 minus delta D by D square, right. Now, the push pull configurations we will show in the next slide. The circuit looks like this. I have a arrangement here. This is grounded. Cf, this is C1, this is C2, this is plus V, this is minus V, this is our output E naught, right. This is our circuit. So, we assume two current, suppose this current is I1, this current is I2 and total current is I, right. And op amps we are assuming is an ideal op amp, so it is not taking any current inside, right. So, if this is the situation, now we can write, let me take a new page, C for the part A or part, sorry, it is not part A, take page, part 1, C equal to epsilon A by D, or delta C equal to, I can write delta C by delta D into delta D, is not it, which we can write quite obviously minus epsilon A. Here the epsilon, please note, it is epsilon equal to epsilon naught into epsilon R, epsilon A by D square into delta D with first order, I mean with approximation, first order approximation. So, this will become again minus C naught into delta D by D. Now, you see, so I can write delta C by C naught equal to minus delta D by D, right. Now, current I actually you can see here I1 minus I2, right. So, which we can write equal to V voltage omega C1 minus omega C2, or which we can write V omega take out, we could be C1 minus C2, right. So, if I take a new page, so the output voltage E naught equal to I minus I upon omega Cf equal to minus V Cf C1 minus C2 equal to minus V Cf epsilon A upon D plus delta D minus epsilon A by D minus delta D. So, this will become V by Cf into epsilon A upon D square minus delta D square into 2 delta D. So, this will become V by Cf into C naught 2 delta D by D upon 1 minus delta D by D whole square, right. So, this we have seen that, so this is our proof actually. So, we have seen that in these cases that how we can use a differential pressure pickup, and I can use a sensor which has a differential output, and how can I connect in the bridge, all those things are we have discussed. Basically in instrumentation you will find these capacitance sensors has basically 3 uses. One is it as a displacement sensors, as you have seen, either permittivity variations or the variations of the area or variation between the separation between the plates, number 1. Number 2 is the level gauge or level sensors. That means level will increase, that means the permittivity will change. So, obviously the permittivity change and the capacitance will change. And third is the differential pressure pickup, which is extensively used in all process industry for measurements of flow. Okay, DP transmitter, this is basically it is called DP transmitter. We have seen that if I change the capacitance of the differential pickup, I will get a change of voltage, that voltage converted to current and transmit it, right. So, these are the basic 3 use of this capacitor sensor as a instrumentation, but we have other applications, as I told you earlier. Also we have discussed also that in this case that we are using the sensor as a pressure pickup, that means sound pressure measurements. Also we can utilize this type of capacitance sensors. Capacitance sensors are very nice to use because it is independent of temperatures and all those things. That is a great advantage of this one. It can be used in the corrosive environments, all those things are very much true. But please note another 2 most important thing of capacitance sensors, that those cables which is connected to this should be we have taken. So, the parasitic insensitive measurements we have to make, because whenever we are measuring very small capacitance value, whether you are using measuring in a bridge or LCR, it does not matter. So, the parasitic capacitance will influence your measurements, and it will pick up the signals like 50 Hz signals and all those things. So, you should be very careful about those parts. So, the non shielding should be very much good, so that if at least one part of the shielding should be grounded, so that the you can make the measurement faithfully. Okay, with this I come to the end of this capacitance sensors. Thank you. Welcome to the lesson 12 of industrial instrumentation. In this lesson, we will basically study flow meters. As you know, the 3 basic process parameters are pressure, temperature and flow. However, if you look at the number of sensors available or the varieties of the particular process parameters like pressure, temperature is much less compared to the flow. The reason is that the flow you will find, not only the type of liquid flowing through the pipe, or it also basically depends on the what type of liquid is flowing. So, depending on that, there are various types of flow meters available and used in the process industry. Sometimes there are volumetric flow, there are sometimes mass flow, there is sometimes positive displacement flow, there is open channel measurement, there is a closed channel measurements. So depending on this, all these circumstances, the number of the flow meters are the highest among all the process parameters if you look at. Now in this lesson basically we will discuss the contents of this lesson rather is the flow meters. We will just give the name of the different flow meters, then we will discuss in details the differential pressure flow meter. Flow transmitter also we will discuss in some brief, and also we will show a separate video on the flow transmitter. Now let us go to the instrumentation lab and look at one of the transmitters, one of the differential pressure transmitter used extensively in the industry. This is a differential pressure transmitter. As you know that in the flow measurements actually the flow is calibrated in terms of pressure. So in all flow meters, I am talking about the variable area like orifice meter and venturi meter. So there is the upstream pressure tap and downstream pressure tap. We have seen in the class that we have shown on manometer sort of thing by which I am measuring the pressure. But unfortunately in the process, actual process, I need some instrument or some equipment which will give some signal that will be transmitted to the control room. Now for that reasons we need some electrical output. So what they do in this case of this differential pressure transmitter, because there are two pressure tap, one is upstream pressure tap and another is downstream pressure tap. Now you can see here this is basically a capacitive type DP transmitter. Here we have an upstream pressure tap, and here you can see the downstream pressure tap. So you can open it and you can connect the upstream pressure tap here. So inside what we have a capacitors with the movable plates. So, and the inside of the two capacitors are plated with some metal. So you will get once the capacitor, suppose this side is high and this side is low, the capacitor's movable plate will move on this side. So I will get a push-pull sort of variations of the capacitance which can be calibrated and in terms of pressure, and ultimately that will be calibrated in terms of flow. Now this is basically these capacitive sensors inside, and there's measurement circuits and signal conditioning circuits are here on this side. You can see here if I open. There is a connection for the signals. You see here that we have positive signals because in the process the output is 4 to 20 milliampere and the supply voltage maximum is 45 volt DC supply, because in all the process, as you know, it's you cannot give the supply voltage much higher. That is also not necessary. And it will give according to the variation. First of all, this circuit will first measure the variation of that capacitance, and that variations of the capacitance will be converted in terms of current, 4 to 20 milliampere of current. So ultimately there's 4 to 20 milliampere of current will be calibrated in terms of flow. But please remember, we have also differential flow meters like pitot tube is also differential pressure flow meters. Elbow meter is also differential pressure flow meters in next sessions which will be discussed. So this ends the lesson 12 of industrial instrumentation.